polynomial functions and their derivatives. So, problem number 1, find the derivative for y equals x squared plus 3x plus 7. Okay, now, what we have learned thus far is the fact that if we want the derivative with respect to x of y, which is dy dx, this is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, now that's what we have been doing before, and that does work, but the power in mathematics is noticing patterns and harnessing them and taking advantage of those patterns. And so we do not want to have to do derivatives by the definition all the time, because it just takes way too long. So we go through and we do this, and we find out that we get 2x plus 3. Okay, so dy dx for y prime is equal to 2x plus 3. And so anyway, there's a little pattern that happens here when we're in this polynomial type of form. And so we do want to take advantage of the pattern that's occurring and not have to just keep on recreating the wheel by doing it the long way. So notice what's happening. Let's look at it term by term. So the x squared became the 2x. The 3x to the first became just the 3. And what happened to the 7? Well, the 7 became a 0, really, effectively. And so one of the first things I do want to point out right now is the fact that the derivative, and it doesn't have to be the derivative with respect to x, but the derivative with respect to something, the derivative of a constant is 0. Okay, so that's always true. Now, why is the derivative of a constant 0? Well, remember that derivatives are slopes of tangent lines, and so if you think of a slope of a tangent line to a horizontal line, because y equals some number is a horizontal line, what's going to be the slope of the tangent line? Anywhere on that constant, it's going to be 0. So derivative of a constant is 0. Okay, now, like I said, the x squared became a 2x, the 3x became just the 3. Okay, let's go ahead and try problem number 2. So if y equals 2x to the third minus 5x, find dy dx, or y prime. Okay, so now, what's really happening here is we are doing the derivative of both sides of the equation with respect to x. So I've got dy dx equals, and I've got the derivative with respect to x of 2x to the third minus 5x. And you just go term by term when it's in this form. Okay. Now, we don't need to show a bunch of work. Really, we just want to kind of go straight to the final answer. But when it gets a little bit more complicated, it's good to know what we're actually doing. So I'm doing 2 times, so the constant times. Now, what's the derivative of x cubed? Well, it's 3x to the second minus 5 times, okay, what's the derivative of x to the first? It's 1 times x to the 0. And so we've got 6x squared minus 5. So there's dy dx. Okay. Now, how do I, what the heck does this thing over here mean? This d to the second power y over dx squared. Okay, well, what's going on there is, well, we just had dy dx equals that. So if I do the derivative of both sides, again, with respect to x, because this is what's really happening. And it's important for us to understand what's going on with the notation. So just kind of take a look at it algebraically. D of dy, so that becomes d squared y. And then dx dx. Now technically it should be really like this. Dx quantity squared. But in math, all the mathematicians, mathematicians are lazy in some ways, because we're saying, okay, everybody understands that the parentheses are there, but we don't really want to write the parentheses. And so therefore, what ends up happening is instead of writing the parentheses, oops, I just erased some other stuff, we just don't write the parentheses and we just say dx squared. Okay, but we understand the parentheses are there. Okay, so, and effectively what this is, we're doing the second derivative of y with respect to x. Okay, well, we just kind of go through and we do the same. We're just doing the derivative with respect to x. So I get 12x minus, and that's a constant, so it's 0. We don't write the 0 in the final answer. So the second derivative of y with respect to x is 12x. Okay, so in general, let's write this out. In general, the derivative with respect to x of a polynomial type of function, okay, we get dy dx equals a times n x to the 1 less power. Okay, moving on. Number 3. If the position function is 3t times t to the third minus 5t, find the velocity and acceleration functions. Okay, well, sometimes we need to do some algebra before we can actually do derivatives. Remember, it's so important for us to remember that velocity is the derivative of the position function and acceleration is the derivative of the velocity. So really, velocity is just the first derivative and acceleration is the second derivative. But sometimes we need to go ahead and do some algebra first. So 3t to the fourth minus 15t squared. Okay, so velocity get a different color going here. So, oh, and by the way, position is a function of time. So I'm going to do the derivative with respect to time. So ds dt, or velocity, is the derivative with respect to time of 3t to the fourth minus 15t squared. Okay, so I would get 12t to the third minus 30t. Okay, the fact that we're saving so much time on this leads us to the position where we can do some longer problems, some things where we don't want to waste our time doing the derivative. So that is particularly helpful, but let's go ahead and do the acceleration right now. To do the acceleration, remember that we're doing the derivative with respect to time of the velocity, or we're doing the second derivative of the position function with respect to time, or dv dt, or acceleration. You can do a of t, or you can just do a. So we're doing the derivative with respect to time of 12 t to the third minus 30t, which is 36 t squared minus 30. And so there's the acceleration function for that particular situation. Okay, problem number 4. If f of x is x squared plus ax plus b, a quadratic function, and g of x is cx minus x squared, also a quadratic function, are tangent to each other at the point 1, 0, find a, b, and c. So, well, one thing that I'm noticing, I mean, and a sketch could be a little bit helpful. You might look at it and you might say, oh, I don't really need to do a sketch, but maybe a sketch is a little bit helpful. And one of the things that I'm noticing, because the function g has a GCF of x, so x times c minus x, it's going through the origin. And we also have their tangent to each other at the point 1, 0, which means that the point 1, 0 is on both curves. So g goes through the origin and it goes through 1, 0. Okay, so g is doing something, and oh, by the way, it's opening down too. So here's g of x. Okay, and if they're tangent to each other at 1, 0, so therefore f of x is doing something like this. Okay, and then they have that point 1, 0 in common. Okay, so they both have the point 1, 0 in common. Don't forget that if a point is on the curve, it must satisfy the equation. Must satisfy the equation. So if I have f of x and the point 1, 0 is on the curve, I get 0 equals 1 squared plus a times 1 plus b. So a plus b is -1. On the other hand, if I have the other curve, 1, 0 is also on that, so 0 equals c times 1 minus 1 squared. So c is 1. Okay, so we've solved for c already now. Let's see, what else can we do? Well, it says they're tangent to each other at that point. Okay, so if they're tangent to each other, let's see, derivatives. Derivatives are really slopes of tangent lines. Okay, so f prime of x must equal g prime of x at the point 1, 0. Probably nowhere else, but at least at that point they're tangent to each other. Okay, so the f prime, we've got 2x plus a and it must be equal to g prime of x, which is c minus 2x and so if I input the 1 comma 0, well really I don't have any place to plug in the 0, but if I plug in the 1, I get 2 plus a is equal to c minus 2. Now wait a minute though. We know that c is 1. So 2 plus a equals 1 minus 2. A equals negative 3. Okay, so we know c, we know a, and so if I plug in a right there, I can get the fact that b is 2. And so there's a, b, and c. Okay, okay, moving on. Got 2 more problems. Problem number 5, write the equation for the line that is normal to the curve y equals x cubed minus 5x plus 1 at x equals 1. Okay, first off, everybody should know the terminology normal or normal line to a curve. So it's perpendicular to the curve. Okay, now derivatives, parallel, or derivatives are the slope of the curve at any particular point along the way. A normal line is perpendicular to the curve at any point along the way. Okay. So the normal is perpendicular to the tangent slope. In other words, perpendicular to the derivative. Okay. So the way we get at the normal slope is through the derivative. So dy dx is 3x squared minus 5. And now I want specifically at this point. So dy dx, this little vertical bar right there means evaluate at, and we're doing x equals 1. So we got 3 times 1 squared minus 5, which is negative 2. Okay, this is the slope of the tangent line at x equals 1. We want the slope of the normal perpendicular, opposite and reciprocal, so positive 1/2. I don't know why I did a plus or minus. I only want a plus. Okay, but we're supposed to be writing the equation of the normal line. I need a slope and a point. So how do I get, I got x equals 1. How do I get the y coordinate? Do I plug it into the derivative? No, you don't plug it into the derivative. You're going to do plug it into the original function. So I'm going to do y of 1, plugging in a 1, I get 1 minus 5 plus 1, okay, which is negative 3. So my normal line, label things, y minus a negative 3 equals 1/2 times x minus 1. Okay, now could you put it in another form? Sure. Could I move the 3 to the other side? Sure. Could you multiply things? Yeah, but is this okay? Yeah, if it doesn't specify otherwise, that's fine. Last problem for today's notes. A projectile is launched upward with initial velocity that yields the position function 144t minus 16t squared, where s is in feet and t is in second. Okay, so units are being included. Using calculus methods, so not some other method that you're aware of, using calculus methods, find the maximum height for the projectile. Okay, well, our position function we can see is a quadratic. And they're saying it's launching upward. Now, unless it's so strong of a projectile that it actually breaks Earth's gravitational pull, it's going to reach a maximum height and then it's going to start coming back down. Okay, so this is S of t. Well, maximum height, what can you tell me about the slope of the tangent line there? Oh, ds dt would be 0, wouldn't it? And that's where the maximum height is going to occur. So we want the derivative, ds dt. What's ds dt otherwise known as again? The velocity. The velocity is 144 minus 32t. So when the velocity is 0, now by the way, as it's going up, velocity has direction. If velocity is positive, and if it's an up-down thing, if positive velocity means it's going up. As soon as it starts coming back down, you're getting a negative velocity. So when you're dealing with up-down things and you're talking about velocity, up is positive, negative is down. Conversely, if you're talking about horizontal or rectilinear movement, positive velocity means that the particle is moving to the right. Negative velocity means it's moving to the left. Keep that in mind for the future. Okay, so the velocity is 0. And so 32t is 144, and t is 144 over 32. And it's nice to have a little calculator, at least of some sort. And we get 4.5. 4.5 what? Well, t is in seconds. Okay, so that's our answer, yeah? No, it says find the maximum height. That's when the maximum height occurs. That's not the maximum height. So how do I find the maximum height? Well, if I plug it into the velocity, I'm going to get 0. I don't want the velocity. I want the maximum height. So we're going to plug it into our position function. So s of 4.5, which is 144 times 4.5 minus 16 times 4.5 squared. And anyway, we get, I have to admit I already worked this out ahead of time. So we do get 324 what? Well, s is in feet, so 324 feet. If units are there, units are important. You must include appropriate units in your final answer to be able to get full credit.